Our solar system is a fascinating place. It's filled with planets, moons, asteroids, and comets all dancing around our sun. But have you ever wondered where it all came from? How did our sun, this giant ball of burning gas, come into existence? This cloud, known as a nebula, was the birthplace of our sun and everything that orbits it. Over millions of years, this nebula collapsed under its own gravity, eventually igniting the star we call the sun. So let's embark on this journey of cosmic discovery together. The most widely accepted explanation for the formation of our solar system is the nebular hypothesis. This theory suggests that the sun and its planets formed from a giant rotating cloud of gas and dust known as a solar nebula. Imagine a vast swirling cloud stretching across unimaginable distances, its contents a mixture of hydrogen, helium, and tiny particles of heavier elements. This nebula wasn't just sitting idly in space. Over time, gravity began to pull this cloud inward, causing it to collapse in on itself. As the nebula shrank, it began to spin faster and faster, like a figure skater pulling their arms in during a spin. This increased rotation caused the cloud to flatten into a spinning disk, with most of the material concentrated at the center. At the heart of this spinning disk, the temperature and pressure soared as the material continued to collapse. Eventually, the temperature and pressure became so intense that nuclear fusion began. Hydrogen atoms were forced together, fusing into helium and releasing enormous amounts of energy. And just like that, our sun was born. While the sun was igniting at the center of the protoplanetary disk, the remaining gas and dust didn't just sit still. The disk was still spinning, and within it, a remarkable process began: the formation of planets. Dust grains, swirling around the newborn sun, started to collide and stick together. These tiny collisions gradually built larger and larger objects in a process called accretion. Over millions of years, these clumps of dust grew into planetesimals, the building blocks of planets. The inner region of the disk, closer to the sun, was hotter. This region favored the formation of rocky planets like Earth, Mars, Venus, and Mercury. Further out, beyond what's called the frost line, temperatures were cold enough for ices like water and methane to solidify. This led to the formation of the gas giants, Jupiter, Saturn, Uranus, and Neptune. These planets grew massive, their gravity attracting vast amounts of gas and dust, becoming the giants we see today. The sun is a giant ball of plasma, not a burning ball of fire. Deep within its core, a process called nuclear fusion is taking place, providing the energy that powers our entire solar system. This process involves the fusion of hydrogen nuclei into helium, releasing a tremendous amount of energy in the process. Imagine hydrogen nuclei as tiny, positively charged particles. Under the immense pressure and temperature in the sun's core, these nuclei are moving at incredibly high speeds, constantly colliding with one another. Most of the time, these collisions are simply deflected. But every once in a while, the nuclei collide with enough energy to overcome their natural repulsion. When this happens, the nuclei fuse together, forming a helium nucleus. This fusion process releases a tremendous amount of energy, which we experience as light and heat. Think of it like a cosmic game of billiards, where each collision releases a burst of energy that travels from the sun's core to its surface and then out into space. Section 5. The main sequence, our sun's prime time. The sun is currently in the main sequence stage, fusing hydrogen into helium. It's about halfway through this stage, which will last another 5 billion years. During this time, the sun will get hotter and brighter. The core will contract and heat up, causing the outer layers to expand. This change is gradual, with brightness increasing by 10%. This will have significant consequences for Earth. Earth's oceans will evaporate and its atmosphere will escape into space. Section 6. Red Giant Phase. The sun's expansion and Earth's fate. After billions of years, the sun will eventually exhaust the hydrogen fuel in its core. When this happens, the core will contract under its own gravity, causing the temperature and pressure to increase even further. This increased heat will cause the sun's outer layers to expand dramatically, transforming it into a red giant star. As a red giant, the sun will swell to an enormous size, engulfing the orbits of Mercury and Venus. Earth's fate is less certain. Some models suggest that Earth may be swallowed by the expanding sun, while others propose that Earth's orbit may expand outward, allowing it to escape this fiery demise. Regardless of Earth's ultimate fate, the red giant phase of the Sun will be a time of dramatic change for our solar system. The Sun's outer layers will cool and expand outward, creating a beautiful planetary nebula, a glowing shell of gas and dust illuminated by the dying star at its center. Section 7. Planetary Nebula, a Cosmic Farewell. As the Sun enters its red giant phase, it will start to shed its outer layers into space. This process is driven by powerful stellar winds that carry away vast amounts of gas and dust. These expelled layers will form a spectacular halo around the Sun, creating what astronomers call a planetary nebula. Don't let the name fool you, though. Planetary nebulas have nothing to do with planets. The name is a relic from early astronomers who, through their telescopes, observed these objects as faint, fuzzy disks that resembled planets. These nebulas are not only beautiful to look at, but they also play a crucial role in the cosmic cycle of matter. The material ejected by the Sun will be enriched with heavier elements produced in its core through nuclear fusion. This enriched material will eventually be recycled, seeding the interstellar medium with the ingredients for new stars and planetary systems. Section 8. White Dwarf, the Sun's final act. After shedding its outer layers as a planetary nebula, the Sun's core will be left exposed. This remnant core, incredibly dense and hot, is called a white dwarf. A white dwarf is essentially the leftover embers of a once mighty star, no longer capable of sustaining nuclear fusion. Despite its small size, roughly the size of Earth, a white dwarf is incredibly dense, with a mass comparable to that of the Sun. Imagine squeezing all the mass of the Sun into a sphere the size of our planet. The gravity on a white dwarf is immense, strong enough to crush atoms and compress matter to incredible densities. Over billions of years, a white dwarf will slowly cool and fade away, radiating its remaining heat into space. This cooling process is incredibly slow, taking trillions of years for a white dwarf to eventually become a black dwarf, a cold and inert object. Section 9. Beyond our Sun, Insights from Stellar Evolution. By understanding the life cycle of our Sun, we gain valuable insights into the evolution of stars in general. Stars, despite their seemingly eternal presence in the night sky, are not immortal. They are born, they live, and they die, just like everything else in the universe. The way stars evolve and their ultimate fate depend primarily on their mass. Massive stars live fast and die young, ending their lives in spectacular supernova explosions. These explosions seed the interstellar medium with heavy elements, essential for the formation of planets and life. Less massive stars, like our Sun, lead longer, more leisurely lives, eventually fading away as white dwarfs. Studying these different stellar life cycles allows astronomers to piece together the grand narrative of cosmic evolution, from the Big Bang to the present day. Section 10. The Search for Life Implications for Exoplanetary Systems. Our understanding of the Sun's life cycle has profound implications for the search for life beyond Earth. We know that life as we know it requires a stable source of energy, like the light and heat from our Sun, and a habitable environment like the Earth's surface. As we discover more and more exoplanets, planets orbiting other stars, we can use our knowledge of stellar evolution to assess their potential for habitability. For example, we know that stars much more massive than our Sun have much shorter lifespans, potentially not providing enough time for life to evolve on their planets. Conversely, stars much less massive than our Sun are much dimmer and cooler, meaning their habitable zones, the regions around a star where liquid water can exist on a planet's surface, are much smaller and closer in. Section 11. Conclusion: a cosmic perspective on our place in the universe. From a swirling cloud of gas and dust to the eventual fading embers of a white dwarf, the Sun's life cycle is a story of cosmic transformation. It is a story that reminds us of the interconnectedness of the universe, how the elements that make up our bodies were forged in the cores of stars long ago. Understanding the birth, life, and death of our Sun gives us a profound sense of our place in the cosmos. It allows us to appreciate the vastness of time and space and the intricate processes that led to the formation of our solar system and the conditions necessary for life to arise on Earth. As we continue to explore the universe, uncovering the secrets of stellar evolution and the search for life beyond Earth, we do so with a newfound appreciation for the delicate balance of conditions that make our existence possible.